Hello students. So moving on further to the portions of the third module. In lecture 11, we shall discuss the analysis of complex AC circuits. In the analysis of complex AC circuits, we should analyze RC series circuit, RL series circuit and Rlc series circuit. In this lecture, we'll be discussing RL series circuit. RL series circuit means a resistance and inductance behavior when they are connected in series across an AC voltage. So that is what we are going to learn in detail in this lecture. Consider an RL series circuit. An RL series circuit means a resistance and a pure inductance is connected in series, and both of them are connected across an AC supply voltage whose instantaneous value is given by V is equal to Vm sin omega t. Since there is a voltage source, a current I will be flowing through the circuit. The same current, it flows through R and L. The voltage across the resistance is given by VR, and the voltage across inductance is given as VL. VR, the voltage across the resistance, is nothing but the current flowing through that resistance into the resistance value, that is IR. Similarly, the voltage across the inductance is VL, that is equal to I into XL, where XL is the inductive reactance. The total voltage V will not be just the sum of VR and VL. It is the RMS values we are calculating. So the total voltage V will be the vector sum of the voltages. That is, V will be equal to square root of VR square plus VL square. Similarly, the total impedance of the circuit Z will be equal to square root of R square plus XL square. The unit of resistance, inductive reactance and impedance will be ohm. Always remember, before calculating the impedance Z, the inductance L should be converted to inductive reactance. The unit of inductance is in Henry. The unit of inductive reactance is an ohm. If you want to calculate an impedance, you have to first convert inductance into inductive reactance. Now, let's look at the waveform to clearly understand the behavior of an RL series circuit. If you see the waveform, there are two waveforms, voltage and current shown. The voltage, it is starting at the zero reference, whereas the current I, it is lagging the voltage. When we had learned pure resistor circuit, we understood that the voltage and current was in phase. Both of them started at the zero reference. Both of them reached the maximum value at 90 degree and so on. And in pure inductor circuit, we learned that the current, it lags the voltage by an exact 90 degree. But in the case of RL series circuit, the behavior of resistance and behavior of inductance is included. Therefore, the current will not start from the zero reference as like in the pure resistor, and it will not lag the voltage by exact 90 degree as in pure inductive circuit. But rather, the current will be lagging the voltage by an angle phi which will be between 0 and 90 degree. Remember, the phase difference angle phi will be between 0 and 90 degree. That is, the current will be lagging the voltage by an angle phi, which will not be exact 90 degree and which will not be 0, but some angle in between 0 and phi. Why? Because both the behavior of resistance and inductance is combined in the case of an RL series circuit. Now, as we have already learned, the instantaneous value of voltage V is equal to Vm sin omega t, and the instantaneous value of current I is equal to Im sin omega t minus phi. It is minus phi. Why? Because the current is lagging the voltage by an angle phi, where phi is the phase difference, which will be an angle between 0 and 90 degree. Now, let's look at the phasor diagram to clearly understand the behavior. We learned that in a pure resistive network, the voltage and current phasors were in phase. There was no phase difference between them. So, VR and the current I, as shown in that first figure, it is in phase. It is 0A. The phasor side is shown. Whereas in the case of pure inductor, we already learned that the voltage, it will be leading the current, or current will be lagging the voltage by an exact 90 degree. That is, the VL term and the current I term has an exact angle of 90 degree between it. Now, you please don't consider 0B at the moment. You just consider only VR and VL. Now, this VL, 0VL is nothing but AB. The same value of 0VL is AB. So, now you have two sides of a right angle triangle, 0A, which is a VR, voltage across the resistance, and AB, that is VL, the voltage across the inductive reactance. So, obviously, the resultant, the hypotenuse term, will give the vector sum of the voltage. That is 0B. V is equal to IZ, where I is the current flowing through that circuit and Z is the total impedance of that circuit. Now, look at the angle made phi. The angle phi is somewhere between 0 and 90 degree. It is not 0, it is not 90 degree, but somewhere between the 0 and 90 degree. That is the phase difference angle phi. So, 0A is a voltage across the resistance which is in phase with the current I. So, both of them are drawn in same alignment. Whereas AB is a voltage across the pure inductor case, VL, that is I into XL. When it comes to RL series circuit, the total voltage will be the vector sum of resistance and inductive reactance. Therefore, V is equal to IZ, the hypotenuse term. OB will be the resultant voltage of an RL series circuit, which is making an angle phi. Now, from this phasor diagram, we can derive the impedance diagram. If that current term I is avoided, you get the exact impedance diagram, where the hypotenuse term is the Z, impedance. Opposite side of angle phi is the inductive reactance XL, and adjacent side of angle phi is the resistance R. So, from here itself, you can calculate the angles. If you want to find out cos phi is nothing but power factor. Cos phi is the adjacent side divided by hypotenuse, that is R by Z. So similarly, whatever angle you want, you can find out from here. Similarly, from this impedance diagram, you will get what is the value of impedance. Z will be equal to square root of R square plus XL square. Next is how to draw that phasor diagram that we have right now discussed. The easiest way is you need to take the current as reference. So the current you draw first. Now the voltage drop across the resistance. That is in phase with current, because resistance always has the voltage in phase with current. Therefore, you have to draw the voltage drop across the resistance VR in the same direction of that current I. After that, you have to draw the voltage drop across the XL, that is 90 degree leading the current. Then the vector sum of the two voltages VR and VL, that will be equal to the total voltage or the applied voltage V, that will be the resultant, the hypotenuse term. This is just a method solved using triangular resultant method, parallelogram law, triangle law. This is just a triangle law resultant finding method. So you get VR, voltage across the resistance is IR, and VL, the voltage across inductance, IXL, where XL is L omega or 2 pi FL. So the total voltage, as we discussed earlier, V is equal to square root of VR square plus VL square, that is square root of IR the whole square plus IXL the whole square. If you take the current term I outside that square root, you get it as I into R square plus XL square, that is nothing but Z. So V is equal to IZ, that will be the total voltage. So I is equal to V by Z, where Z is square root of R square plus XL square. This is nothing but the impedance, the total opposition offered to the flow of alternating current by an RL series circuit, and its unit is always measured in ohm. Next, we shall calculate the phase angle, that is phi. Phi you may calculate easily from the phasor diagram or from the impedance diagram. In RL series circuit, we have already discussed that the current will be lagging the voltage by an angle phi. So that can be given by the equation. Either you can take cos phi or you may take tan phi, whichever. Tan phi is nothing but opposite side divided by adjacent side, that is VL divided by VR, or it is IXL divided by IR, or simply XL by R. So you will get phi as tan inverse XL by R. Similarly, if you want, you can take the cos phi power factor also. Cos phi will be R by Z. Therefore, phi will be equal to cos inverse of R by Z. Now let's move on to the power calculation in an RL series circuit, just like we have calculated for pure inductance, pure resistance, pure capacitor, etc., the simple AC circuits. If the applied voltage V is equal to Vm sin omega t and the current I is Im sin omega t minus phi, the instantaneous value of power is instantaneous value of voltage into instantaneous value of current, that is Vm sin omega t into Im sin omega t minus phi. So you get it as Vm Im by 2 sin omega t minus phi sin omega t. You just open bracket it. So final answer, you get it as two terms. First term is Vm by root 2 Im by root 2 cos phi. That is a constant part. And the second part is actually a double frequency component. That is Vm by root 2 Im by root 2 cos 2 omega t minus phi. Now since this it's a cos 2 omega t term, it is a symmetrical term. The average value for a complete cycle will be definitely 0. Now going on to the average power consumption. The average power consumed in the circuit over one complete cycle will be given by the average of the constant part and the average of that double frequency part. The double frequency part, only term remaining will be Vm by root 2 Im by root 2 cos phi. Vm by root 2 is nothing but Vrms. Im by root 2 is Irms. So you can write it as the power is equal to Vrms Irms cos phi. The Vrms, you simply denote it as V. Whenever you see a term V and I, it is just RMS value, those are given. If it is a maximum value, definitely the subscript M will be given. If no subscript is given, usually remember this case while you are doing the numerical problems, if no particular suffix is given, then just understand it is the RMS value that is given. Okay. Now the cos phi term, it is known as nothing but the power factor. You may calculate it as cos phi is VR by V, that is R by Z. The definition is it is the ratio of resistance to the impedance of AC circuit. Now if you put this value of V and cos phi from this equation, then you will get that P is equal to V is nothing but IZ into I into cos phi is R by Z. So you get it as I square R. From this equation you will clearly understand that the power consumed or the average power or the power used by the circuit is only used by the resistive component. There is no term of inductive reactance coming into the scene. Therefore, that we have already discussed in the previous lectures of resistive inductance and capacitance also. The power will be only consumed by the resistive element, that is dissipated in the form of heat, that we have already calculated for the resistive circuit as P is equal to Vi cos phi. Whereas for purely inductor or purely capacitive circuit, the average power consumption is definitely 0, which means that no power is actually utilized by an inductor or capacitor. It is returning that power in effect. Therefore, the power consumption or power absorption happens only across the resistive element. Now we may look at the waveform. Here three waves, voltage, current and power is shown. The voltage, it is starting from 0 reference and ending at 2 pi, one complete cycle. Now the current waveform, you may see that it is starting after an angle phi from the reference, which means the current is lagging the voltage by an angle phi. You may see that it is not 0, it is not exact 90, but an angle phi in between 0 and 90 degree or pi by 2. Now let's calculate the power. As we have already learned, the power is the product of instantaneous value of voltage and instantaneous value of current. So for the instant 0 to phi, for 0 to phi, the voltage is positive, current is negative. Therefore, the power will be positive voltage into negative current, therefore negative power. And look at the magnitude also. The magnitude also will be very less, because the magnitude of voltage and the magnitude of current from 0 to phi angle is small. Therefore, the power is also small. Now from phi to pi, from phi angle to pi, the magnitude of voltage and the magnitude of current both are higher and both of them are lying in the positive half. Therefore, the power, it will be in the positive half, because it is positive voltage into positive current. Similarly, from angle pi to the next phi phase difference, the current is in the positive half cycle, whereas the voltage is in negative half cycle. Therefore, the power will be negative power and the magnitude will be lesser. But from phi to 2 pi, both of them, current and voltage, is in the negative half. Therefore, negative voltage into negative current will be giving the positive power, and the magnitude is also higher. So now let's do a problem. An RLC circuit, it contains a resistor and an inductor. The resistor, it's having a value of 6.5 ohm. The circuit is connected across 120 volt and has a current flow of 12 ampere. What is the inductive reactance? In such kind of RL series combination questions, two important things that you should definitely draw is its circuit diagram and its phasor diagram. Without these diagrams, whatever calculation you are going to do will never fetch you marks. So first, let's draw a circuit diagram. Question says it is having a resistance and inductance. So draw a resistance and an inductance and connect it across a AC voltage. The value of the resistance is 6.5 ohm. L, you have to find it out. The current, it is given in the question as 12 ampere and the voltage is 120 volt. Next is phasor diagram. In phasor diagram, I have already said that the voltage across the resistance, it will be always in phase with the current. Then the voltage across the inductive reactance, it will be 90 degree with the current. And the total voltage V will be the resultant of the voltage across the resistance and voltage across the inductive reactance. So to complete the phasor diagram, you should write the magnitudes also. So now let's start to calculate it. First, you need to find out what is the total impedance. Total impedance of a circuit Z is equal to total voltage V divided by total current I. That is 120 divided by 12. You give 10 ohms. Therefore, the total impedance Z is equal to square root of R square plus XL square, that we have already learned from the impedance triangle. Therefore, XL is equal to square root of Z square minus R square. That is square root of 10 square minus 6.5 square. You get it as 7.599 ohm. Question is to find out the inductive reactance alone. But if it was to find the inductance, then you know XL is equal to L omega. So L is equal to XL by omega, or XL divided by 2 pi F. In this question, the frequency is not explicitly given. If it is not given in the question, you may arbitrarily assume it as 50 Hertz. So you get the answer as 0.024 Henry. Now to complete the phasor diagram, you should write the magnitudes of those voltages also. For that, the total voltage V, it is already given in the question as 120 volt. So nothing to calculate. Now the voltage across the resistor VR, it is nothing but IR. So I is 12 into R is 6.5. You get it as 78 volt. Now VL, you can find out by two ways. Either you can use equation VL is equal to IXL. That is 12 into 7.599, you get 91.19 volt. Or you may use the equation VL is equal to square root of V square minus VR square. Why? Because the voltage, total voltage is the vector sum of the voltage across the resistance and inductance. Now, if the question also asks you to find out what is the power factor is cos phi. Cos phi meaning adjacent side divided by the hypotenuse of the phasor diagram, voltage diagram or impedance diagram. Here we have already drawn the phasor diagram, so we can use from this phasor diagram itself to find out cos phi. So cos phi is equal to adjacent side is VR divided by the hypotenuse V. That is 78 divided by 120. You get it as 0.65. That is the power factor of this circuit. If you want to find out the phase angle phi, take cos inverse. So you get it as 49.46 degree. Now let's do another tutorial problem. This is a bit different from that earlier case. You should be very careful with this question. A non-inductive resistor of 10 ohm is connected in series with the choke coil. This choke coil is where you have to give the stress. A choke coil meaning it is not simply an inductance. A choke coil in itself is a combination of resistance and inductance in series. having an effective resistance of 1.2 ohm and it is fed from 200 volt 50 hertz supply. Current flowing through the circuit is 8 ampere. Calculate the reactance of the choke coil, inductance, voltage across the choke coil, power absorbed by the choke coil, power absorbed by the non-inductive resistor and the total power absorbed. So as said earlier, for such kind of problems, the two primary things that you should definitely draw is a circuit diagram and the phasor diagram. First, let's move to the circuit diagram. As the question says, it has a non-inductive resistance of 10 ohm. So there is a resistance R that is equal to 10 ohm and a Chaulk coil. I have mentioned it earlier, a Chaulk coil meaning it is a combination of resistance and inductance in series. If you consider or take the choke as an inductance alone, you will end up in a wrong answer. So always remember a Chaulk coil meaning there is a resistance and an inductance in series. Well, the values of Chaulk coil, I have taken it as R1 and L. So the entire elements, they are connected across 200 volt 50 hertz and a current of 8 ampere. It's flowing through this circuit. So this is how you draw a circuit diagram. Now coming on to the phasor diagram. Phasor diagram is a bit complex than the previous problem. So kindly pay attention. First, let's draw the phasor diagram of the choke coil. Then we shall build up the non-ohmic resistance also to the phasor diagram. So first let's see the triangle ABC. How the triangle ABC has resulted. So first let's draw the current I. Because I you have to take it as reference. Now the voltage across the choke coil resistance R1. The resistance voltage will be always in phase that of current. That is why in the same direction of current I have drawn the VR1. For time being, do not look at the magnitude, just look at the denotations. To the current I, in phase I have drawn the voltage across the resistance of the choke coil, which is R1. So VR1 you have drawn. That is BC. Now you have to draw the voltage across that choke coil inductance. That is VL, which is equal to IXL. That will be always 90 degree to VR1. So I have drawn it as AC. Why I have drawn this AC towards upward direction? Because the voltage, it leads the current I by an angle 90 degree, or you may say that the current lags the voltage by an angle 90 degree in the case of an RL series circuit or in the case of an inductance. So I have drawn AC. So you have two sides of the triangle BC and AC. BC is the voltage across R1 and AC is the voltage across L. So using the triangle law, you can find the resultant voltage of this choke coil by completing this right angle triangle. So the resultant vector will be AB. Okay, the resultant vector will be AB, that is the voltage across the choke coil alone, which is making an angle theta with VR1. For time being, I have just marked an angle theta. Even if you don't mark it, theta is also fine, but you have to definitely mark the phase angle phi. So thus we have drawn the phasor diagram of the choke coil alone, which is BC, AC and the resultant AB. Now from this resultant AB, we are going to construct the resultant of the total circuit. We are having one side as AB, that is the resultant voltage of the choke coil. Now the voltage across the resistance 10 ohm. Always said earlier, the voltage across the resistance will be in a line with the current I. So I have drawn the voltage phasor in alignment with the current I, that is OB. So right now we are having the voltage across the resistor and the resultant voltage of the Chaulk coil OB and AB. So the resultant of this triangle, which is not a right angle triangle, will be OA. That is nothing but the total applied voltage 200. That makes a phase angle phi. You can see the phi, it is not 0 or it is not exactly 90 degree. It is some angle between 0 and 90 degree. Okay, so you must understand OA is the total resultant voltage, that is the applied voltage 200 volt, and AB is the resultant voltage of the Chaulk coil. Now we shall find the magnitudes of these voltages. Okay, so first is, let's find what is the voltage drop in the Chaulk coil. For that, first you need to find what is the voltage across the non-inductive resistance 10 ohm. That is VR, capital VR. That is IR. So the current flowing is 8 ampere into the resistance magnitude 10. 8 into 10, you get 80 volt. So you may write VR in the phasor diagram as 80 volt. Now voltage across the Chaulk coil resistor. That is R1. That is I into R1. R1 magnitude is already given in the question as the effective resistance of Chaulk coil as 1.2 ohm. So voltage will be 8 into 1.2, that is 9.6 volt. So you may write VR1 as 9.6 volt in the phasor diagram. So what will be the total voltage across these resistances? That is OC will be equal to OB plus BC. OB is 80, BC is 9.6. So the total voltage across the resistances alone will be 80 plus 9.6. That is 89.6 volt. Now voltage drop across the Chaulk coil. That is, first you should find out what is the AC term. Right? AC is equal to square root of OA square minus OC square. In order to get AC term, what you have to consider? You have to consider the outer triangle. Okay, you have to consider the outer triangle. I have again drawn that phasor diagram, a second phasor diagram with OC, AC and OA. OA, it is nothing but the applied voltage 200 that you already know. OC, that is the total voltage drop across the resistances. Calculated it as 89.6 volt. So two values we are already having. So you can find the unknown quantity AC. That is square root of OA square minus OC square. So you get it as square root of 200 square minus 89.6 square. So you get VL, that is nothing but AC, as 178.8 volt. Now what is XL? VL divided by I. That is 178.8 divided by 8. So you get it as 22.35 ohm. So the magnitude of the inductive reactance is 22.35 ohm. Then second question was to find the inductance. XL is equal to L omega. Therefore L is equal to XL by omega. Omega is 2 pi f. So L is equal to 22.35 divided by 2 into pi into 50 hertz. You get it as 0.07711 Henry. Third question, to find the voltage across the Chaulk coil. Meaning you have to find what is the resultant voltage of the Chaulk coil, that is AB. from the phasor diagram, first phasor diagram, if you want to find AB, that is the square root of AB is a hypotenuse. So it will be square root of BC square plus AC square. BC is 9.6 and AC is nothing but the VL that we have calculated it as 178.8. So you get the voltage across the Chaulk coil, that is AB, as 179.1 volt. Next is power absorbed by the Chaulk coil. This is a very tricky question. A Chaulk coil, it has a resistance and inductance. We have already learned that an inductance will never consume power. So there will be no power absorption by the inductance term. The power will be consumed or dissipated across the resistance only. So power will be I square R1, that is 8 square into 1.2. 1.2 is nothing but the effective resistance of that Chaulk coil, which is already given in the question. So it is 76.8 watts. Now the power absorbed by the non-inductive resistor, that is 10 ohm resistor. So that is nothing but I square R, that is 8 square into 10. That is 640 watts. And the total power absorbed, that is the power absorbed in that resistor 10 ohm and power absorbed in the Chaulk coil, that is 76.8 plus 640, you get it as 716.8 watts.